This is lesson 2 of maybe 13, who knows, but quite a few lessons. Working on orienteering maps and trying to figure out just what the heck you're doing. Hopefully I don't steer you too far astray. Lesson 2, I want to talk about coordinate reference systems, and I'm talking about this early because it's the very first thing you should do in setting up a map. I've had my fair share of lumps I've taken when making maps because I didn't understand anything about this, and I've got all kinds of data from different coordinate systems and couldn't figure out how to make them match up, and it really caused chaos. So the main thing I've learned from all of my years of making these maps is that you want to start your map with a coordinate reference system you know and understand and stick with it. Furthermore, I recommend that as a club everybody use the same one as well. There's really not a lot of reason to pick one over the other in a lot of instances. As long as you stick with it and you understand it, most of the time the orienteer will never notice the difference between one type of projection versus another. So let's talk about some of this stuff. First thing I want to talk about is two terms, GCS and PCS. And GCS is going to stand for Geographical Coordinate System, and PCS is going to stand for Projected Coordinate System. And it's kind of important to understand these two to some degree. I'm going to use the term coordinate reference system to describe the combination of both of these things. Typically they are used together to describe the way the map is drawn and where things are on the map. The geographic coordinate system itself specifically is designed to tell where the data is on the Earth, and the projected coordinate system is used to describe how to distort the map in order to make it look good on a 2D piece of paper or on a digital display. The geographical coordinate system, what it does is it initially models the Earth itself. The big round sphere, they take the size and shape of it, and then they subsequently take what they measure to be the size and shape of the Earth and then place items on it at agreed to locations. And they measure those locations in degrees, and you're familiar with them as latitude and longitude. So it's a round unit of measurement that are angular measurements. They're not linear and straight lines like you would expect because you're looking at 2D maps, but they actually are round. So these items that are drawn on the map at the agreed to location based on the way they model the Earth, we call that entire item and concept a datum, D-A-T-U-M. A lot of people use all these terms interchangeably, but that is the real idea behind a datum, which is we got the Earth modeled, this is where things are, and this is how we measure it. But, what happens if the time we measure the Earth, we weren't really as specific as we wanted to be, or we weren't as accurate as we wanted to be, or we made a mistake, or we decided that the actual shape of the Earth needs to be more specific in one place versus somewhere else because of a reason that may not be obvious to the person at the time they made the initial model? Well, what happens is you have to redo the Earth model. And what happens to all the stuff that you drew that was on that Earth? Yep, they're in the wrong spot. So you have to create yourself a whole new datum and find some sort of way to offset everything from the initial model to the second model. So the GCS, or the Geographic Coordinate System, is what ties your coordinates to the location of the actual item on the Earth. In order to get this geographical coordinate system, you have to know three things: the datum, which is based on the Earth's shape, the angular unit of measure, which is like the latitude, longitude, and of course you need to know the prime meridian location. What you need to know as a student or someone learning this lesson is that the geographical coordinate system is sort of the foundation and it's part of the overall coordinate reference system. They're used to describe things where they are on the round Earth. So what is a projected coordinate system? How is that different? Well, a projected coordinate system is what we use in order to make a flat map. What I would recommend is that you take a look at this drawing here and wrap your head around what we have to do in order to make this round ball flat and appealing to the eye. You see here where we take a globe and we stretch it out and cut it open. There's really no way to make it perfectly flat. The places where there's missing parts of the globe, there's gaps there, and we'd have to join those gaps somehow by stretching the globe from one side to the other, and in doing so it would cause distortion of the map some way or shape. Now we wouldn't, in this example, we have the cuts at the polar ice caps, and we are stretching it around the center of the Earth. But we could do it in another way too. We could cut it at the equator, or we could cut it linearly, or make a cylinder out of it. Cut the top off and just make the inside stretched out, but leave the top flat somehow. There's really an infinite number of ways that you could distort this. And this overall concept is simply called projecting. The type of projection that we use and most people who hike and do land navigation use is called UTM. And UTM stands for Universal, what is it again? Universal Transverse Mercator, I believe. Yes, I remember now. Universal Transverse Mercator. And Mercator is a type of projection, and Transverse Mercator is basically the variation of that. And you see how this works is that they break the Earth up into 66-degree zones and then label them 1 through 60, starting from the date line going around the Earth to the east. Washington is in zone 10, and specifically we're in zone 10 north. Things below the equator in 10 south. So it just turns out that this 10 north is the zone that I recommend you use and all of our club use for orienteering purposes. Specifically, this EPSG, which is a code to specify even variations within the UTM itself. This is a specific UTM zone 10 north, EPSG 26910. So let me show you a few examples of how these things might work in real life. Okay, when you first start a map in Open Orienteering and you say create a map, it'll ask you a few questions. And the first thing is the scale. If you want to do a 1 to 4,000 perhaps, or a 1 to 10,000 scale map, you select that the first thing. And the very first thing you should do when you get presented with this screen is do nothing until you select Map and Georeferencing. And the problem with this screen is that you kind of have to know a little bit about georeferencing in order to fill it out. You can select UTM from here and then fill in your code of 10 north. But as you will see in a minute, there's actually a lot of different UTMs that exist out there. I recommend you fill in the EPSG code of 26910. And then we're going to get into what this means. And we'll fill in all this stuff later in a later lesson. But the very first step you're going to do is have to understand this and then kind of wrap your head around it and memorize it to some degree. So let's go to Qgis for a second and look at some of the things that you can do in Qgis. So here we are in Qgis, and again I have the Big Fin Hill Park map opened up, and I have a couple points on the map that I'd like to point out. This first point, 72 point A, is located right above the other point called 84 point A, which is an airplane over here by the parking lot. Both of these points are physically in the same spot on the planet Earth. Now, the first point, 72 point A, is actually in the datum of WGS 72 UTM Zone 10, an EPSG code of 32210. The other point is recorded in a CRS of WGS 84 Zone 10 North. So different EPSG code of 32610 versus the geographical reference system of WGS 72. Different datums, but they're in the same spot on the map. So what would happen if I took the first point and said, no, this is actually supposed to be WGS 84. So I can take that data for that layer and say, I'm sorry, I put the wrong reference information there. I did not mean to select this EPSG. This data was actually recorded in WGS 84 data. Let's put that in the system, and now you see what just happened to that point. The point now moved, not very much, not a significant amount, but it's in a different spot. And that is a graphical representation of what Datums can do for you. The point is now described completely different. In this case, we're talking about maybe 50 meters tops, but it could be significantly more based on where you're at on the planet and what datum differences you choose. Also, I want to point out that that coordinate reference system that I applied to that point only. But this map itself has its own coordinate reference system, which is displayed down in the bottom right-hand corner. The map is in EPSG 26910. So the GIS information system, the software that's used for this, is taking everything that's stored in whatever data format you tell it it's stored in, and then reprojecting it and replacing it on the map based on this projection system that I've defined for the overall project. I could redefine the overall project as something completely different, and it will take all that data and reproject it to that. Essentially, it's doing all of the magic of the software for me, which is really nice. So I can just select anything I want and apply it, and everything still looks like it's the right space. So that's essentially what the coordinate reference system is doing for us. I want to talk about a few of these coordinate reference systems as we're sitting here, because it's kind of important. Let's talk about UTM specifically. I mentioned I'd like to use UTM 26910, but if you'll see, there are a lot of UTM zone 10s available. There's a UTM zone 10 that is NAD 83 HARN datum, and that's a high accuracy datum. There is the NAD 83 NSRS 2007 3717, and the list sort of goes on and on and on and on. Why did I decide that I wanted to use 26910 as my reference? One, I believe the NAD 83 datum is better for North Americans because the the reference plane should not be moving relative to the other types of datum, such as WGS 84. WGS 84 is a global datum, and the NAD 83 is a North American datum, so our reference plane should be stationary. That may not be technically true, but for our purposes it is. A lot of the data I have accumulated is in this NAD 83. I do have some data that's in the NAD 83 HARN, but most of the data is in the NAD 83 already. And so most of my maps have been started in that format, and so I prefer to keep them all in that format going forward. I believe if I was to switch to a different format, I would use the NAD 83 2011, which is a slightly higher accurate and becoming more common of a data source in Washington at least. That would be, as you see the picture here, it shows me that it's a nice little UTM stripe right down the west coast for a little distortion, and that's very useful for all the maps we make up in this area. Find your own datum that you want to use based on where you're at in the world, but I certainly recommend UTM if you're in America, and if you're somewhere like Great Britain, you can use the local Great Britain grid system and any other system that's specific to your area. So that's pretty much it for the idea behind the coordinate reference systems. It's simply finding the one you want, understanding what each data you have is stored in, and then using that data going forward. I'll explain to you how to use Qgis later on to save the data in whatever format you want. In this case, I showed you I have a point stored in WGS 72 data, but I really want to keep it in a different format, store it in a different format in my project folder. There's a simple way to do that. In Qgis, you can just right-click on the data you have, and you can export those features that you have into a file location, which you could specify here, and then you could change the datum to whatever you want, and it will reproject it and place it in the correct geographical position. I typically save my file name such as in a format such as this. That way, whenever I actually go to use it, I know exactly what EPSG code it's in. It makes it very handy. I recommend you follow a convention similar to this, where you put the actual EPSG code into the title somehow. All right, that's it for this lesson. Hope you got something out of that. The next lesson, we're going to start going over gathering data, where to get the data from, some basic sources I use, and some ideas. and then how to maybe manipulate some of that data in QGIS. And we'll keep going forward after that to create our base map data with that information. And if you have any questions, please contact me at tahomaorienteering@gmail.com. Thank you.